Welcome to Tech Talks, a production of the Emerging and Innovative Technologies Committee in the Environmental and Water Resources Institute, EWRI. The objective of the committee is to identify technologies that have the potential to affect fundamental changes in environmental and water resources science, engineering, and management. In this series, we've invited 3 guest speakers to share their projects with a brief presentation, followed by a conversation with our committee leadership. Myself, Dr. Marcus Aguilar of the City of Roanoke's Stormwater Utility, Professor Sierra Young of North Carolina State University, and Mr. Marcus Quigley, CEO of EcoLucid. In Session 1, we'll hear about Mr. Adam Arispa's use of artificial neural networks to improve urban watershed modeling. Session 2 will continue the conversation with Mr. Matthew Garcia's implementation of machine learning to create a next-generation flood alert system. Finally, we'll learn about assessing the risk of lead contamination in private drinking water wells using citizen science data and predictive models from Mr. Mohammad Ali, Khaksar Fasaee. I hope that you enjoyed the Tech Talks as much as we did. Please feel free to recommend ideas for future Tech Talks in the comments.
All right, welcome everyone to one of our Tech Talk series hosted by the ASCE EWRI Emerging and Innovative Technologies Committee. My name is Sierra Young. I'm currently the vice chair of the committee, and also on our call is Marcus and Mohammad. Marcus?
Hey guys, I'm Marcus Aguilar. I'm currently the chair of the committee this year, and I am a research engineer at a mid-sized stormwater utility in Southwest Virginia. So it's Roanoke, Virginia. Mohammad?
I'm Mohammad Ali Khaksar Fasaee. Currently, I'm a PhD student at North Carolina State University. I'm working in the STSA research group with the supervision of Dr. Emily Bergland. I'm happy to present my work for you.
Great, we're happy to have you. So yeah, today we're going to hear about Mohammad's work on lead contamination in private wells and then move into some Q&A at the end. So Mohammad, feel free to take it away.
Thank you. So as Sarah said, today I'm going to talk about the risk of lead contamination in private wells using citizen science and predictive models. As we already know, lead is a toxic metal that can be harmful for human health, even at low level of exposure. Therefore, EPA sets the maximum contamination level goal is 0 for drinking water. Unfortunately, the governing agencies are not responsible for the quality of water in the private wells. Therefore, the owner of private wells may face an elevated risk of lead, especially for the houses built before 1986, because there were some lead materials in the plumbing. Okay, now in this research, we are trying to develop a model to predict high water lead levels to inform layperson, to the owner of these houses. In order to answer that, we are first trying to explore an existing dataset that describes lead levels in private wells to understand the connections between the variables and the lead. And finally, we are trying to develop some machine learning approaches based on different level of inputs for predicting the lead contamination. Okay, for our predictive models was built based on the dataset that was collected by the Virginia Household Water Quality Program during 2012 and 2017. They collect water samples and conduct a survey to collect some information about the water. As you can see here on the map, we demonstrate the spatial distribution of the contaminated samples that were defined that water lead levels above 15 parts per billion based on the EPA's guideline. The color shows the ratio of the contaminated samples, and the numbers on the map show the number of samples that were collected on that county. If I want to talk about the dataset properties, I could say it's a relatively large size dataset. It's about 10,000 samples on the Virginia. And if I want to talk about the attributes that I could mention 4 major categories of data that we collect, the water observation, such as the color, taste, and the odor of the water, the system characteristics, such as water treatment type, plumbing time, and the well type. Also, we get some information about the geographical property as a county and the aquifer. And finally, we do some testing and collect the water quality, which we call it the laboratory data. We usually collect the pH, hardness, and the lead concentration in the first draw after 6 hours of stagnation, and 21 more chemical properties. And we use these data sets to explore to find the relationship between the attributes and the lead contamination. The predictive model was constructed based on two different algorithms, the Bayesian belief network and the ensemble of decision trees. We choose these two. First, I'm going to describe these two methods, and then I'm going to say the reason that why we choose these two methods. First, the Bayesian belief network is a probabilistic graphical representation of the causality between multiple events by showing the directed graph. As you can see here on the bottom, it's a simple naive-based structure of the BBNs that we have one target variables, and the predictors, or which is called the parents, are connected by a directed edge. And the main advantage that the reason that we use the Bayesian belief network is that it gives us the information about the dependency and the connection of the predictors and the target variables. On the other hand, the ensemble of decision tree is a combination of the simple decision tree that can predict the contamination or classify the contamination. The reason that we use the ensemble of decision tree is that it gives us more robust and generalized predictability over a single decision tree. As you can see here, we have a bunch of single decision trees and their prediction, which is yield to a final output or classification. Okay, so as we talk, we are going to describe investigate several types of inputs. First is as a survey data, which is provided by the user and which is provided by the user, and also the location data, which is the aquifer and the county, which we retrieve this information from the addresses of the households. And finally, we exclude the water quality to see what's the performance of the simple model that we could build. In this chart, I'm going to show you the recall versus F1 score. Usually we see the accuracy, but since we are dealing with the imbalanced data set, which means that about 10% of the samples are contaminated, so we have to use different metrics to measure the performance of our predictive models. Recall shows the number of contaminated samples that accurately identified by the predictive models, and the F1 score is a little complex metric that is an alternative for the accuracy for the imbalanced data sets. Higher values are better. So we could see here the performance of EDT on the blue and the BBN on the green color. And also we studied the effects of location property. We built a model with the county and aquifer for BBN, and we only built a model with county and the survey data, aquifer with survey data, and just survey data on a circle. You could see as we remove the geographical property, the performance drops. And the EDT performs much better than the BBN because we have higher values for recall. It can easily capture the contamination. Now let's see the structure of the predictors of the BBM. We focus more on the BBM because it shows us the dependency between the variable. We use the naive weight with forward selection to remove the unnecessary features. As you can see here, it has 39 nodes, 38 of them are parents or predictors, and one, the target variable, which is a LED. And on the table, we could see all the 38 predictors. Usually they are Booleans, which means that, for example, the blue string is a Boolean variable that is either presented or not presented in the observation. Now, as we saw the performance was low, we tried to come up to an idea to improve our performance. So we are going to include the water quality data in the prediction. So we have seen that in the market there are several at-home kits. So we try to find an easy way to measure water quality parameters from the users and report these discretized water quality parameters. So we come up with the idea of using at-home kits. We studied two types of kits. The kit one which has 14, which can measure 14 parameters, and on the right side we could see the number of parameters and their corresponding levels. So people can easily use the strips and measure the water quality and then report it. And the other one, which is a more simplest kit, it only measures two water quality parameters, pH and hardness. And now we do the same analysis using BBN, and which is shown by triangles, and sorry, BBNs are shown with the circle, and also the EDT on the with a triangle. In addition to the kit 1 and kit 2, we use data-driven methods to discretize and use them in the context of our models. As we could see, the performance improves to 80 for the recall and 60 for the F1 score, which on the bottom, we could see the result of survey, the best survey model, which is about 30% for the F1 score. So by adding water quality parameters, we have seen that the performance improves from the simplest model, which is the green one, to the more sophisticated or more the kits that can measure 14 variables. The blue one, the performance of both F1 recall and F1 improve. And ideally, the best one is the one that is used with the data-driven model. Now let's see the structure of the best BBN model that come up out of the kit one. It has more variables, and also especially we could see that the water quality parameters that uses in the as the predictors. Again, it uses naive weight, which is the simplest BBN structure with the forward selection, and we have 59 predictors to predict the water quality. In order to summarize the current research, I could say that the ensemble of decision tree provides higher recall value compared to the Bayesian belief network, which means that it can predict more contaminated samples compared to the Bayesian belief network. However, in terms of accuracy, how many of them are contaminated, the BBNs outperforms EDT. And one of the advantage of BBN is that it provides the linkage between the variables. Also, in the survey model, the geographical variables are very important. Absence of any location data decrease the performance of the predictive models. And by adding the water quality parameters, our performance significantly improves. As I could say, for the F1 and the recall, for both EDT and BBN, it's about 20 to 30% improvement. And if we use even at home water quality tests, the performance improves about for the recall and F1 about 20% compared to the survey model. And also we need further research to investigate and understand the errors associated with at-home kits Thanks for your attention. I hope it's about 10 minutes talk.
Yeah,
Yeah.
that's great. Thank you so much. A really good overview and super interesting research, and something that I find also personally relevant, as our house is on a well. So now I'm thinking I need to go get a water quality testing kit.
Yes. As a
But
part of this program, this research is that we could collect these water quality parameters on a website, as you can see here in this. Okay, here there is a. Okay, we're trying to develop a questionnaire that people can use this test script and send us the image, so we could easily analyze the test script and provide some feedback to the users. Is a part of our research.
oh, that's so interesting. So you are working towards having people take a picture and do perhaps automatic, because one of the questions I had was, is there, like, how much subjectivity is in looking at and matching up these color strips on the scale? So yeah, that's, I think, a really neat concept to kind of have an automatic strip, measurement kind of approach.
Yeah, as you can see under this on the right side, there is a QR code that you can easily take a photo and send it to this QR, and it's automatically analyze your strip based on the scale and then provide some feedback for you.
No, that's really neat. So, I mean, it seems like these water quality parameters are important predictor variables. Do you have any idea, and then also geographic location, but any kind of sense of what the most important variables are in this approach out of the 60 or so that you had included in those models?
Yes. As a part of research, we try to find the feature importance. Which one are the most important? I could say the copper, as a rule of thumb, just the copper and the pH are the most. The combination of the copper and pH can provide about 50 to 60% of the performance in either models. So just knowing these two parameters can give us more information about the lead contamination.
No,
But when you say the copper, you mean the concentration of copper as you're showing here on the screen, not the presence of copper plumbing.
No, I mean that the concentration of the copper. Yeah.
Okay.
The water, on the water quality parameters, we usually focus on the concentration.
Okay. Yeah, that's really interesting. I was wondering the same question that Sierra just asked, and I think it's, what I was thinking about is in terms of like the ease of someone at home filling one of these things out, it would be advantageous to narrow it down to the most important parameters, because then that means you can only ask a subset of your questions and it
Yes.
fill it out, and you can potentially get more data out of it because someone could more easily fill the survey out. So
Yes, as a part of this program is to, because answering 68 variables or even more is hard for the users. So we are trying to build it down into several steps. If you need more information, you have to provide more input variables. So we are trying to find the basic or the essential or vital parameters, input parameters at the beginning, like the copper, based on our analysis, we could find the most significant features. So trying to group them as a level 1 for the prediction. And then if you need the in order to improve accuracy of the prediction, the users must provide more information. Yeah, we are trying to develop these kind of predictive models based on the number of input variables you can receive a prediction.
Is there any potential for some of the variables that were perhaps proximity to industrial operations? Is that information, to the best of your knowledge, publicly available in any sort of GIS data set that you could compile? I saw things like fruit orchards and coastal operations and industrial plants and that list. If maybe the person didn't need to fill that out, but that could be kind of established as a data set layer. I'm just curious.
Right now, we ask the user to provide this information, but we are trying to build it based on their location. We could easily retrieve this information on a website. So as a part of the website application, yes, we are trying to include these features or these input variables from the web, retrieve it from the addresses. Yes,
Neat.
we are trying to do that.
Thanks.
Yeah, that's cool. So one comment to that, and then a question is, I think Virginia's DEQ has a data set of the Virginia's pollutant discharge elimination system permits that you could probably fetch and put into a GIS, so that you wouldn't have to ask that question in the form. So that was the comment. And then, can you go back to your map? I think it was like the second slide, maybe.
Mm-hmm.
And I'm interested in this because I, of course, live in Virginia. My county is the one that has the 288, Roanoke County. So
This one.
I'm looking at your sort of heat map here, and obviously one of the things you mentioned is that geography is important. So what I'm seeing is Piedmont. Like, Piedmont percentages look a little higher, and maybe some coastal plain counties are a little lower, and maybe some of the mountainous counties up against West Virginia are a little lower. Have you guys thought about like what it is about geography that's driving it? Is it geology? Is it something else that's happening that could be causing this? Like, what do you think about that, Mohammed?
Honestly, I haven't focused on the geography or the aquifer. We call it aquifer. But I'm thinking about that if there are some contaminated houses near each other, because we can see here the numbers are high, and also the percentage ratio is also high. So maybe there is a correlation between the nearest neighbors, the number of contaminated households, for example, in 10 miles radius with my house. So we are focusing more on the distance and nearest neighbors property in our model. We are trying to build a model based on the nearest households property to estimate the risk of lead. But for the geography or the aquifer, no, I haven't looked in depth on that.
I have a question, just getting towards the end here and thinking like big picture. When you go to implement this in a web-based tool, which I think would be awesome and something that is definitely needed, as I think water quality in private wells is a pretty big issue. So let's say your model, outputs a particular risk of lead contamination, maybe at a certain level, or maybe just whether it exceeds the, some threshold. If that risk, depending on what that risk is, are you going to make a recommendation for that household to go get further testing, or are you just going to provide that risk threshold and let the homeowner decide for themselves whether 30% risk is enough to go get further? I guess what's your ultimate goal in kind of providing a recommendation?
What's the ultimate goal is to provide not only the information about the risk, also feedback. So and recommendation. If the risk is high, we strongly recommend them to do laboratory tests to make sure that the drinking water is safe or not. And based on the levels and based on the prediction, we do provide some recommendation.
Do you have plans to expand this to North Carolina or any other?
Yes, we do. Recently, we are just doing some paperwork to use this information to use this data. Whenever the paperwork has been accepted, easily we applied the framework on the Virginia to the North Carolina, and the ultimate goal is to build or extend this work for the whole nation, for the whole US.
Oh, that's really cool.
Sierra, do I have time for one more?
Yeah, absolutely.
Okay, cool. All right, so your question a moment ago just about the use of the data and how it gets internalized, I guess, in the homeowner's decision-making process is really interesting, I think. So recently I was reading that Realtor.com now includes flood risk data on their, when you're like looking at a house, you're interested in like buying a house, you can click on a property and it will show you like what the potential flood risk over a certain lifetime is. I guess I'm like kind of thinking about that as like, okay, what if that data becomes available for lead? I mean, is that like a possibility where you start talking about people looking at homes for purchase, but then realizing, based on this data set, there's like a reasonably high level of lead, or at least we think there may be a reasonably high level of lead in the well water. So either I don't buy the house, or I buy the house, but the inspector says you got to get this plumbed into, to a local water supply, for example, instead of using a water well. So just comment on that, kind of explore that a little bit if you would.
Sorry, so what was the question? I missed that.
Well, I just thought you would have, think about like the potential application there for your project. If on Realtor.com, lead risk is a variable that now a potential homeowner could see as a result of your work. Yeah, like what do you think about that? Is that something that could happen in the future? Is it valuable? Is that data something that could be problematic in like the home buying, property buying space that, people would say, I don't want that data available because I want to be able to sell my house. Does that make sense?
Exactly. Yeah. As a part of this project, as you mentioned, how could we share this information to the public? Because there is a problem, especially for the property wars. Many people concerned about that. And probably we could not share this information to we could share the information with the homeowners, but we could not share it publicly available, or it's hard to say. Only I could say that I have seen that for the Flint, there is a map, or the household map, with a high resolution that shows the house has lead plumbing or not. But for the other stuff, I think it's very hard, and there are some challenges about the worth of the household and the information that you provided, because as you said, maybe it's affect the house price. So I think at some point we cannot, hopefully in the future we could have access, or we could have permission to share it publicly, but right now we have to provide this information only to the homeowners.
It's good. Really interesting. Thank you for the presentation, Mohammad. This has been really
Thanks.
Yeah, thank you all for a really great discussion and a really interesting talk. I'm curious, and we'll want to follow how this project continues to evolve, as it is of particular interest to me. So yeah, it looks like we're at the end of our time. So thank you again, Mohammad. We really appreciate you taking the time to talk to us today.
Thanks for inviting me.
Thank you.
Thanks, Mohammad.